course of optical instrumentation. So, in this lecture series, this is our 5th lecture, and in this lecture we will discuss about optical activity and optically active materials. With this, we shall also discuss about few effects that are based on optical activity. Okay. So, today's topics are optical activity, electro-optic effect, magneto-optic effect and Acousto-optic effect. So, what is optical activity? There are certain materials through which if we pass a plane polarized light ray, then the plane of polarization rotates by a certain angle. This property of certain materials of rotating the plane of polarization is called optical activity, and such materials are called optically active materials. This property of optically active materials is very useful in various applications. So, it is the ability of a substance to rotate the plane of polarization of a beam of light that is passed through it. Okay. So, for example, this is unpolarized light beam. Okay. So, this is unpolarized light beam coming from source in this direction, and this is unpolarized light. So, you can see the electric vector, it is vibrating in all the directions, but the direction of the vibration is perpendicular to the propagation of the light ray. So, light ray is coming in this direction and electric field is vibrating perpendicular this direction. Okay. What is this? This is a polarizer, or we can say polarizing filter. This is a vertical polarizer. Okay. So, when this unpolarized light pass through this polarizer, vertical polarizer, then it will be converted in plane polarized light. So, now you can see this is a vertical polarizer. So, now the electric field vector is vibrating perpendicularly, or all the other vibrations of electric field vectors are stopped by this vertical polarizer. Now, you can see this is a optically active material. So, when this light ray passes through this material, this plane of polarization is rotated by a certain angle. Okay. So, this property of these materials is called optical activity, and such materials are called optically active materials. Now, if we again put a same vertical polarizer in the path of that ray, now the intensity of the beam that is coming outside will be less. Okay, because only the component of the vector that is perpendicular to this axis will pass through this analyzer, or we can say vertical polarizer. Okay. So, when a beam of plane polarized light is incident normally on a crystal plate of quartz. So, quartz is an optically active material. So, when a beam of plane polarized light falls perpendicular on the quartz crystal that is cut perpendicular to the optic axis, it is found that the emergent beam is also plane polarized. So, the light that is coming out is also plane polarized, but its electric vector vibrates in a different plane. Okay. So, now the plane of polarization is rotated by a certain angle, and this angle depends on various properties and various parameters. Okay. Vibrates in a different plane from that of incident light. Okay. So, this is optical activity. Materials that exhibit this property are called optically active materials. Okay. Now, if this plane of polarization is rotated clockwise or towards right, such crystals are called right handed. If the plane of vibration is rotated in a clockwise direction, looking against the ongoing light, then such crystals are called right handed or dextro-rotatory crystals. Okay. If the rotation is in clockwise direction, then such crystals are called right handed or dextro-rotatory. On the other hand, if the vibration is rotated in a counterclockwise direction, okay, counterclockwise direction, then such crystals are called left handed or levorotatory crystals. Fine. So, this was about optical activity and optically active, introduction of optical activity and optically active materials. Now, based on this property, there are few effects. First is electro-optic effect, second is magneto-optic effect, and third is Acousto-optic effect. So, one by one we shall discuss these three effects. Now, what is electro-optic effect? If we apply electric field across an optically active materials, then the orientation of electron changes, okay, and it also changes the refractive index of that material. So, let us see, when an electric field is applied across an optically active material, the distribution of electrons within it is distorted. Okay. So, due to this applied electric field, the distribution of electron changes, it gets distorted, so that the polarizability and hence the refractive index of the material changes anisotropically. Okay. So, its polarizability and refractive index is changing according to the applied electric field. Now, in this case, if we pass a plane polarized light through this material that is subtended across a electric field, then its refractive index changes. So, now the ray, the angle by which the vibration rotates also changes, and this change depends on the applied electric field. If the change in refractive index varies linearly with the applied electric field, it is known as Pockels effect. If the refractive index is changing linearly with the applied electric field, then it is called Pockels effect. And if the variation in the refractive index is proportional to the square of the applied electric field, then it is called Kerr's effect. Okay. So, these effects are against the names of the scientists. Okay. So, there are two effects, one is Pockels effect, one is Kerr's effect. When the refractive index changes linearly, it is called Pockels effect, and when it is changing proportional to the square of the applied electric field, change in refractive index is proportional to the square of the applied electric field, then it is called Kerr's effect. So, change in refractive index can be given by this equation, it is given by this equation. Change in refractive index is equal to R into applied electric field plus P into square of the applied electric field, okay, where R is linear electro-optic coefficient, linear, and P is quadratic electro-optic coefficient. Okay. So, this is due to Pockels effect, this one, it is due to Pockels effect, and the second term it is due to this effect. Okay. In solids, linear variation in the refractive index associated with this term is known as Pockels effect again, while the variation arising from quadratic term is Kerr effect. In some material, this one is more dominant, and in some materials this one is more dominant. It depends on material to material, it varies from material to material. So, this is a pictorial representation. In this material, potassium dihydrogen phosphate, it is an optically active material. So, the crystal of this material over here, it is placed over here, and an electric field is applied across this material. From here, a unpolarized light beam is coming, and we have kept a polarizer, vertical polarizer over here. So, what it will do? It will convert this light into plane polarized light. When this light beam is passed through this material, then the light that is coming outside is rotated. Okay. So, for example, if we take this is the light beam. Okay. So, now when it gets passed through this crystal, what we have already seen in optically active materials. So, this vibration, this plane of polarization rotates through a certain angle by a certain angle, that is theta. Now, this rotation depends on this applied electric field. So, we can modulate, if we have an electrical signal, message signal, and if we apply that signal across this crystal, for example, this voltage, this is our message signal. If we apply that signal across this material, and if we pass a plane polarized light ray, then the rotation of this plane of polarization, it will depend on this message signal. So, we can modulate an electrical signal on a light signal or an optical signal. Okay. So, this is a very good application of this effect. So, this is a electro-optic modulator. What is this? This is the diagram of an electro-optic modulator. Electro-optic modulator. Okay. Why? Because we can modulate, we can superimpose electrical information, the voltage signal, the voltage information, amplitude information of an electrical signal on the plane of polarization of a light signal. Fine. Next is magneto-optic effect. So, if we apply magnetic field across this optically active crystal, then also its refractive index is affected, and the rotation, now the angle of rotation, it depends on the applied applied magnetic field. Okay. Presence of magnetic field also affects optical properties of some materials, some optically active materials. Okay. So, there are various magneto-optic effect. Out of these various magneto-optic effect, there is one that is called Faraday effect. It is the simplest magneto-optical effect in which refractive index of material changes when subjected to a steady magnetic field. So, the refractive index is changing when material is subjected to magnetic field, like when it was changing when it was subjected to electric field. So, again the same thing, when a beam of plane polarized light passes through a substance subjected to magnetic field, its plane of polarization is observed to rotate by an amount proportional to the magnetic field. Okay, proportional to the magnetic field component parallel to the direction of the propagation. Fine. So, there is a equation. So, this angle of rotation, it depends on 3 parameters. It is equal to V into B into L, where V is a constant, that is called Worded constant, B is magnetic field parallel to the direction of propagation. So, the component of magnetic field that is parallel to the direction of propagation, and L is the path length, the length of the material through which the plane polarized light ray is passing. Okay. Also, the angle of rotation is independent of the direction of propagation. It was not there in electro-optic effect, but in magneto-optic effect the direction of rotation is independent. Okay. Let us see how, through a diagram, with the help of a diagram. So, what is this? This is called Faraday optical isolator. Faraday optical isolator. So, this is the optically active material and there is a magnetic field applied across this material. Okay. So, this is unpolarized light beam coming from this direction. Okay. So, you can see the electric field vector is vibrating in this direction, and also it will be also vibrating in all the directions that are perpendicular to the direction of propagation. Okay. So, there is a vertical polarizer. After that, what we are getting? We are getting a vertically polarized light ray and the vector is vibrating vertically. So, when it is passed through this optically active material that is subjected to magnetic field, it is rotated. You can see the field, the angle is rotating by how many degrees over here? 45 degrees. 45 degrees. Okay. So, if we put a analyzer, or you can say 45-degree polarizer over here, then we will get 100% intensity. But if we put a vertical polarizer or horizontal polarizer, the intensity will reduce. Only the vertical component will pass through that polarizer. Okay. So, this rotation is independent of the direction of propagation of light ray. So, in this example, the light ray is propagating in this direction. Okay. So, the vibration, the plane of polarization is rotating 45 degree in this direction. If the light ray rotates in this direction, then also it will rotate in the same direction. Okay. Then also the plane of polarization will rotate by the same angle and towards the same direction. So, it will be not like if it is traveling, light is traveling in this direction, then the rotation will be in the opposite direction. No, it will be again in the same direction. So, what we can do? We can use this effect to make a isolator. So, what is isolator? So, no light will come back, no light will be reflected, all the light will go in the forward direction and it will be absorbed over there. Okay. It is very useful, it is very beneficial in research, for research purpose and also for optical communication, in optical communication fibers. Okay. So, what we can do? We can apply a mirror over here. Okay. So, what we can do? We can put a mirror over here. Let us put a mirror here. So, this is a mirror. So, what will happen? this light ray will be reflected and will come back in this direction. Okay, it will come back in this direction. It will be passed through this analyzer. This light ray will get passed through this analyzer because this is already capped at 45-degree angle. So, this is 45-degree polarizer, and the light ray will travel again through this crystal. So, when this light ray travels again through this crystal, what will happen? It will again rotated by 45-degree. Okay. So, again it will be rotated by 45-degree in this direction. Okay. So, the vertically polarized light will get converted in horizontally polarized light. Okay. So, it will be rotated 90-degree, 45-degree in this direction and 45-degree while coming back. So, it will be rotated by 90-degree. So, over here you can see we kept a polarizer, vertical polarizer. So, if a horizontally polarized light will fall on this polarizer, what it will do? It will block all the light and it will not allow any small amount, even minute amount of light to pass through it. So, we will not get any light coming in this direction. So, this is called optical isolator. So, you can see this half part is shown in this diagram. So, this is a 45-degree polarizer. So, we get a 45-degree polarized light like we are getting here. Okay. And the same optically active material with the same amount of applied magnetic field is kept here. So, when this light ray comes here, so you can see over here, now we are getting horizontally polarized light. Okay. So, the light is polarized in horizontal direction. So, now this is a vertical polarizer kept here. So, no light comes through this polarizer. Okay. So, this was about magneto-optic effect and Faraday's optical isolator. Next and last is Acousto-optic effect. Acousto-optic effect. Now, we have seen that the refractive index changes when we apply electric field, also changes when we apply magnetic field. Same thing happens if we apply a mechanical strain wave, okay, or a sound wave, that is an acoustic signal. Change in refractive index of a medium caused by mechanical strain accompanying the passage of an acoustic wave through the medium. This change is caused by photoelastic effect, which occurs in the material on the application of mechanical stress. Now, this change again, the refractive index changes if we apply acoustic signal, okay, or mechanical stress. Change in refractive index is proportional to the square root of the total acoustic power. So, change in the refractive index of optically active material, it is proportional to the square root of this mechanical power, okay, total acoustic power. So, again through this we can superimpose any acoustic signal on any optical wavefront, okay, as shown in this figure. So, this is a incident light beam, this is an incident optical wavefront, parallel optical wavefront coming in this direction. This is coming in this direction, okay, through this material, and over here there is an acoustic wave applied on this material from here, okay. So, you can see there are crest and throws. So, it is travelling in this direction. According to this acoustic wave, the distribution of electron is changing and refractive index is changing. So, accordingly this wave front that is coming over here is modulated and diffracted. Okay. So, this effect is called Acousto-optic effect. So, diffracted light beam diameter over here. Okay. So, we have seen in this lecture what is optical activity, what are optically active materials, and what happens if we apply electric field, magnetic field and acoustic wave across these optically active materials. We can superimpose this information on optical beams through this effect. Okay. So, thank you.